Hi everyone, thank you for coming. We will start in around 8 minutes on top of the hour. Thank you for joining. And hi, Srikant. Am I saying the name right? I hope I am. How are you today? Thanks for coming. If you like to share the room, feel free to do it. That's what I'm doing in the meantime. And this is in the meantime, also, if you would like to check out the lab website from Dr. Kolachalama, you can check on research, what he's doing in general. So yeah. Oh, I'm sorry that you don't know English. Do you have a translation app maybe that can translate the content? I hope you do. Hey Manas, hey Kelly, hey Shriyasta. We will start in around 4 minutes. Welcome and yeah, bringing you up. Feel free to unmute. How are you today?
Good,
Welcome.
good, Katerina. How are you? It's a very nice topic. I just did my. I think I finished my understanding dementia course in May. So I'm so happy you brought such a nice topic.
Oh yeah, thank you so much. Yeah, this topic is very important to me because with the mental health crisis around the world is getting worse. I think it's really important, and yeah, I'm really
Exactly.
curious what. Yeah.
Exactly. Like I said, Katrina, I'm also like starting my startup based on this, and I'm looking into really aging care and teaming up with a lot of people in the US at the moment and even Europe, because the aging population, even in India, like people are honestly not aware. And the population of India, like when I run rooms on mental health, they really don't understand, like, they really, the society, it just brushes it off. They don't understand that the crisis is at a clinical level, and we don't have enough doctors given the population, and there is not enough uh, trained professional care workers for this aging population in general. So that's you are like doing a very great thing by hosting this room. So yeah, nice to see everyone else also in the room and in the panel.
Hi there. Can you hear me?
Yes, we can hear you. Hi,
Hi.
welcome.
Hi.
We
Thank
would,
you for setting this up.
yeah, thank you so much. We'll start in 2 minutes, and in the meantime, we were talking how important this topic is. So yeah, thank you.
Thank you. hmm I've asked some of my lab members to join as well. I think, unfortunately, this time is a bit tricky because some of them, I think, are just starting the semester. So I hope they'll join. If not, I'll take it over.
Oh, I'm sorry. We could have made it at a different time.
No
Maybe
problem.
maybe next time. Maybe
Yes.
in a few months or so, you have time to come back, and then we do it at a time where it's better for your students. Maybe in the middle of the semester at a different time of the day.
Yeah, that
Yeah.
sounds good. But I can try my best.
Yeah, and tell your students this is recorded, so if they listen to this on Clubhouse, like if they just make an account, you know, what is really good about it is that the links we share here in the chat and also on top, they are still available. So whenever we mention something that we are sharing this link for further reading or something, all of this is still active in the recording. So that's why we really like the Clubhouse recording version.
Great. That sounds good.
Yeah, I think we can slowly start, and welcome Victoria, welcome Joyce, and welcome everyone.
Good morning. Thank you. So nice to see everybody.
Yeah, hi.
Look forward to meeting you and hearing more.
Okay, great. I'm so happy the team is together.
Yeah. With these giant mics. Do you notice the giant mics on screen?
Right, but I heard it's a bug, so
Yeah,
they will go
yesterday.
back to normal. Uh, I don't know if anyone noticed, but the microphones are gigantic.
We're in the land of the
But,
giants for a while.
yeah.
But that's a distraction, sorry.
Yeah. Okay. Okay. Let's slowly start, and then I'll switch over in a minute to your paper, so
hmm
people can, when you talk about it, can follow along. For now, we have the lab website on top of the room if people would like to check it out. But before we start, let me introduce you to everyone so people get to know you a little bit. So, welcome everyone to Science Society, and a special welcome to our guest speaker here. And I hope I'm pronouncing your name right, Dr. Wiyaya Kolachalama.
Okay.
Was that correct?
Pretty
No.
close. Pretty close. I'm
How would you say it?
I'm Vijay Kolachalama.
Kolacham, Kolachalama.
Yes,
Okay,
that's right.
okay, good,
Vijay.
good, good.
Yes. You can
Vijay.
call me Vijay. Yeah.
Okay, Vijay. Perfect. Okay. He's associate professor at Boston University, and he did his bachelor of technology and at the Indian Institute of Technology in Aerospace, Aeronautical, and Astronautical Space Engineering, which is really cool. And he did his PhD at the University of Southampton and mechanical engineering. And later on, he did his postdoc, one of his post at the MIT, at the Massachusetts Institute of Technology. Then he was a principal member of technical staff at Draper, and and he's still a co-founder also of deeppath.ai, which is really interesting. Please check it out. And he, as I said, he is now the associate professor in the Department of Medicine at Boston University School of Medicine, and founding member of the Faculty of Computing and Data Science. And he won several honors and awards, including the Evans Junior Faculty Merit Award, and the Toffler Scholar in Neuroscience Award. And yeah, so thank you so much for being here. And before we usually start, Victoria asks a few interview questions, if that's okay with you. And in the
Sure.
meantime, yeah, perfect.
Thank you
Thank
for the
you.
nice introduction, Katharina.
Okay, Victoria, the stage is yours.
All right, thank you so much, and that was fascinating to hear the introduction of your accomplishments, Vijay. So
Thank
this
you.
question, yeah, thank you so much. We're so happy to have you here. My questions are to not only lead us into your discussion, also to share a little bit about the person behind the research. It helps us to follow along, maybe with a new kind of interest. And so the question is, if you can reflect on your life and maybe find a place that you noticed that you had a particular interest in science, or that science was something you felt a strong connection toward. And this could be in your childhood or really any time in your life. And any from a person or an event or class or whatever strikes you as, as what the answer might be for you.
Oh, it's a very good question. I don't think there is a simple answer to this because I've been very fortunate to uh, get motivated at many stages of my life, during many stages of my life. I think the primary source was my family, my parents, and actually my grandmother, because I grew up in her house for many, many years. So she was the one who taught me the value of education and for many years. And I think with her blessing, I was able to do well in school. And I think it just carried forward. And every time I just moved to the next grade or moved forward in my career, I was just able to meet some really nice people, some great mentors, great teachers, and just took what I could during the whole process. So it's very hard for me to point at one single individual or one single event, but I clearly have to give the credit to my grandmother.
That's so amazing. It's really it's important to hear what was instrumental in your motivation, and you mentioned the word support, that she was there supporting you and that you had her blessing. And
Yes.
it's when we think about our own interactions with people in life at any stage, then I think it's encouragement to consider the effect that we have on each other as far as support and encouragement goes. The importance of that, I don't think, stops when you leave childhood. So thanks to your grandmother.
Yes.
and
Yes.
and then also, perhaps, is there something that you felt was maybe along the way to the work that you're doing now? Were there any noteworthy surprises or challenges that you would like to share with us?
Yeah, I mean, I grew up in India, and I, like many other kids, most of them, were inspired to, take up on STEM mainly, science and engineering mainly, and I just followed the similar path during my school. I wanted to, do something in science and technology and engineering, but I never got exposed to medicine for a long time. In fact, even during my undergraduate, I was just doing my engineering, and I never knew there was a subject that was biomedical science. So only during my later years of my undergraduate, I came to know that there is a whole discipline called biomedical research. So at that point, I started to began appreciating what biomedical science was, and I think one of my mentors was pointing at doing rocket science was child's play compared to working on how things work within the body. So that was kind of an interesting quote by a faculty member in my college who was actually an engineer and was working on space science. But at that point onwards, I thought of looking at what biomedical research was, and I think that was a time when I began to appreciate biology and medicine, and slowly began to think about how to move in that direction, because it was, I came from a completely different background, science, engineering. Like Katharina said, my undergraduate degree was in aerospace, so I was never exposed to biology until that point. Only just basic in school, but that was not so much. But the biomedical research was something that fascinates me even today.
So there's so many common threads there that I hear when I ask our guest researchers this question, a common thread is that people had had questions and they wanted to pursue their schooling and their work to find solutions and answers. And it's also speaks to how important it is to acknowledge what you just shared, that you didn't know, you weren't aware that there was this discipline. However, in the big picture, if we scope back, then of course everything is related, and it doesn't matter if it's recognized in a school setting by a class or career title with that name. It already exists, and so it's so important that you were able to locate that, so you could then focus your work on that which interests you at the moment, and bring all of your experience there. So thank you so much
Yeah,
for sharing
yeah. I
this.
mean, I still am. Thank you for the note. I am still fascinated, and I always, when I look back at what I did, sometimes it's always hard to connect the dots, but I somehow do it.
Yeah, that's why I believe that, from one perspective, something might look like chaos, but from another perspective, as you say, you connect the dots and everything makes sense in the mind of the person who's walking that path.
Yeah, yeah.
This,
Thank you. Well,
thank
I
you.
hope I can continue to do biomedical science research for
Yeah,
some more time.
you will, and we have no idea where you'll go next because that's up to you, and there's no reason to put boundaries on anyone's work, and so at this point, um, I will turn over the mic to you, and you may
Hmm.
begin your talk, and then we, the moderators here, can help people if you would like to have a Q&A following your talk, or you'd like to have the Q&A drive your talk along. Either way, we're here to assist, and sometimes friends in the audience will place questions in the room chat, and if they do, we can tell you what those are as well, so you don't need to worry about that. You can just relax and enjoy delivering your presentation. So thank you.
Sure. Thank you. Thank you for setting this up again. So I think just to make sure I understand, so the links are available for people to take a look at the paper, right?
Yes. Oh, sorry, you, Katarina, go ahead.
Yes. Oh, no, it's fine. Yeah. Yeah, the link is on top of the room. It's
Okay.
yep.
Okay. I guess my plan is to just use the manuscript as a template to go over my talk. I think it's somewhat easier for me to take a look at the manuscript and then talk about what we did, because sometimes I feel like slides may not carry all the information, but clearly in the manuscript we tried our best to describe all the aspects. But of course I can't cover everything in the hour, but I'll try my best. So I guess the just to give some background about where we are and what how this ended up becoming a paper. We've been kind of working in the field of Alzheimer's for a few years now. I think the main credit actually goes to my students, who I think have worked extremely hard for I would say 2 years to get this paper out. And I think when we are thinking about AI and Alzheimer's, I think one thing that I always see is how can we actually work on such kind of a multidisciplinary question sitting in a specific research lab, right? And fortunately, in my case, I have mainly two kinds of students who are part of my lab. One of them is a computer science student who is getting a PhD in the Department of CS, and for that person to get a PhD in computer science, they have to make advances in computer science because they have to advance the algorithmic knowledge. They have to think about computational aspects. They have to just do some excellent work in CS. And on the other hand, I have, fortunately again, MD students who are the future doctors, who want to be doctors, and they are fascinated about AI, and they want to work on some interesting questions that are clinically relevant, but at the same time they also want to explore AI, right? So, and when I put these two types of students in the same room, fortunately sometimes magic happens, and in this case, both of them, actually not just two, but a group of people, a group of trainees, work together to work on something interesting. Because if you look at the field of AI, I think especially AI in medicine, there are many things that are happening, many cool things that are happening, starting from diagnosing cancer all the way to diagnosing infectious disease. So our interest was mainly focused on dementia, because we think it's an interesting question. And although there was a recent approval of a drug called aducanumab by a company called Biogen, there is still not an effective treatment that can tackle Alzheimer's disease. So there are millions of people around the world who I think have Alzheimer's disease and dementia. I think dementia is a very broad category. I think Alzheimer's disease is the common cause of dementia. About 60 to 70% of people who have dementia also have Alzheimer's disease. And there are a few other ways of getting dementia. I think Parkinson's is one, and Lewy body dementia, frontotemporal dementia. There are many other variants, but Alzheimer's disease is the most common form of dementia. And we are talking about millions of people getting affected. And the disease is kind of, a very strange condition because, for example, if somebody has pain, or if somebody gets a fracture or something, they have pain and they sort of seek help. But when it comes to these kinds of neurodegenerative conditions, the care management is very complicated. And staying with a person, whether it's a doctor or whether it's a family caregiver, uh, managing the person who has dementia is pretty challenging. And especially if the dementia is severe, it's even more challenging. Um, but I think when you look at how to manage this condition, hopefully there are going to be more therapies in the future. But at this point, the best option is to identify the condition early on so that you can provide better care management. And for us to identify dementia early on, we need tools, we need expertise, we need all kinds of different examinations done on these people, and we have to somehow figure out a way to process all that information to assess the patient's condition. But unfortunately, there are two things that are happening that is kind of troubling. One is that more and more people are living longer, which is great. But on the other hand, these kinds of aging related disorders are on the rise. So there are more people who are getting diagnosed with dementia, more people are probably suffering because of dementia. And on the other hand, there is a shortage. There is an extreme shortage of medical expertise that can essentially evaluate the patient in various clinical settings around the world, right? So there are two things that are happening, and I think the projection is that the situation is going to only get worse because on one side, many people are going to be affected. On the other hand, there are going to be fewer and fewer doctors who have the potential to actually do something on these patients. So those two factors have motivated us to think about other ways to uh, figure out how to diagnose this person and how to accurately diagnose the cognitive status of people who may have dementia. And and because we were working on AI approaches, we thought we were going to start building some AI algorithms that hopefully can take in information and potentially can diagnose accurately the cognitive status of these individuals. So that was kind of really the motivation to work on this project. I mean, this is not the very first paper we published. We have done a bit of work in the past. This is kind of really a follow-up to a few other papers that were published in the past. And this paper is special because we have built upon what we received as feedback from our previous work, and the goal was to sort of basically come up with a tool that can accurately diagnose a person along the dementia spectrum. So, and typical clinical workup is that if suppose if somebody is living in Boston or New York City or one of those big cities, they have access to a lot of resources, but technically those resources are not available in all locations, right? So, based on my discussions with some clinicians, some neurologists who see these patients on a daily basis, they have told me that you have to imagine a situation in a typical family, a person, let's say a 65-year-old female or a male, who is living with their family happily, and suddenly um, the person starts behaving weird. In other words, they turn on the stove, they forget to turn it off. They are going out, they sort of kind of forget where they're going, and slowly and steadily the family basically starts observing what's actually happening. And over a period of 1 or 2 months, what, maybe we should seek a opinion. And after those 2 months, they basically try to maybe set up an appointment with a family provider, like a primary care physician or someone, and then take the person to the primary care physician. And the primary care physician has some skill in terms of looking at the condition, and then if they have some kind of suspicion, then they will say, what, I do what I could, but maybe you should go and seek a consult or a specialist, seek a specialist to look at this person. So typically in the United States, if you want to get a neurologist appointment, I'm not talking about specialized neurologists, I'm talking about general neurologist. The wait time is a few weeks, right? It doesn't happen the next day. So we're talking about, let's say, January 1st, something begins to happen with that person. By the end of February, they decide to take the person to a primary care physician. You get an appointment somewhere in March, and that time the primary care physician says, okay, you know what, go and get a neurologist appointment, which might take another couple of months. So we're already talking May for the neurologist, for the general neurologist to actually see the patient. And the general neurologist obviously has more skill than the primary care physician because they have the expertise on the brain, and they do some examination. They collect all the family history, the patient history. They are capable of administering some cognitive tests, and based on whatever assessment they can do, they may have some suspicion on that this person may have some form of dementia or some kind of a cognitive impairment. And typically at that time, they also want to either send the patient for an MRI image or MRI scan, or maybe even recommend a special consult to someone called as a behavioral neurologist, who is the expert in terms of actually diagnosing somebody to have Alzheimer's or other forms of dementia. Right? And again, that appointment takes a few weeks, and hoping that in the best case scenario, the neurologist provides their information and their opinion, and at the same time, you're getting an MRI. And the collection of all this information will probably go to that behavioral neurologist, who, in a few weeks from that point, can maybe see the patient again and then finally make an assessment. Right? So that's the typical workflow. I wouldn't say this is the best case scenario, but at the same time, this is probably a practical scenario that happens. So from the time when things become deteriorated until the point you get a diagnosis, a proper diagnosis, we're talking about 6 months or more, right? So, and the belief in the community is that sometimes these things are very progressive disorders, and by the time the person gets diagnosed with dementia, it's probably already too late. You can't do much on those patients except for hoping to manage them in the best way possible, right? So there are these inefficiencies, and I'm assuming some of these inefficiencies exist even outside the US, in places where, what if you don't have a neurologist at the right time in the right place? What if you don't have a behavioral neurologist at the right time in the right place? So what are we going to do in those scenarios, right? So these are all practical challenges. When I'm describing and when I'm thinking about it, it feels that we could do something about it, and that kind of has been our goal, which is how can we, as computer scientists, how can we really help, not just do research, but how can we really help solve this problem, right? And it's not an easy problem to solve, and it's not a trivial thing to solve, because there are so many practical aspects surrounding real world scenarios. If you want to simulate a computer to create a real world scenario, it's very hard, right? Because there are so many nuances here, right? So, but again, we made some progress. We began sort of appreciating all these different stages that exist, and we are slowly begun to sort of not only, first of all, innovate on the machine learning and the AI side of things, but also think about these practical scenarios on how to actually solve the problem. And it's a long process. We are not even close, but I think we made some really important strides. And this paper is one important stride where we have shown that we can reasonably come up with a reasonably good AI-based model that can perform dementia assessment using data that is routinely collected in a clinical neurology setting. So, which means the AI framework here, if you slowly scroll down to maybe figure 1 in this paper, you may see the workflow that we have described, which is we collected data from 8 different cohorts, and these cohorts are studies that are done on people with dementia and Alzheimer's disease around the world. And I think these are short forms mentioned in the figure here. So there is a cohort from Australia. There is a cohort from Massachusetts. There is a national cohort, and there are several clinical cohorts that have dedicated themselves to look at dementia and related disorders, right? So we were fortunate to get access to data from all these different places, and we initiated collaborations with many different clinicians around the country, actually outside the US as well. So we have been very careful, and we have also been very selective in terms of picking our collaborators. So for this project, we began working with physicians in Boston, neurologists in Boston Medical Center. We also then connected with neurologists at the University of Nebraska Medical Center. And it's an interesting place because Nebraska is kind of really in the Midwest, and it's a very busy center, and it sees a lot of patients from the rural areas, right? So that's an interesting population. And the physicians have that experience, although the data didn't come from the rural population, but the physicians were part of the study. And we also collaborated with folks from Stanford and also from Beijing. Um, and all these physicians actually have helped us to evaluate the model. I'll come to that in a second, but I think the figure here is kind of really showing that we've been able to collect data from all these different cohorts. And when I say data, I'm talking about clinical history, demographics, MRI imaging, their functional assessment, which means every patient undergoes some cognitive testing. All those things were collected on all these people. And then our goal was to somehow create or unify information coming from imaging data, non-imaging data, and somehow figure out a way to first of all understand if this patient has, healthy cognition, or mild cognitive impairment, which is another stage, and if not, dementia, right? So that's typically the spectrum, right? When people talk about dementia spectrum, they usually talk about people who are healthy, or people who have some form of mild cognitive impairment, or somebody who has dementia. But if somebody has dementia, then they also want to know whether that dementia is because of Alzheimer's disease or due to something else. So that's kind of really the machine learning framework, which I think was innovative by itself, where we were able to combine information from all these different modalities of data, and the machine learning model was able to make a two-stage prediction. The first stage was, okay, given this data, at where do the person fall along the dementia spectrum? Is it normal cognition or mild cognitive impairment or dementia? And if the model predicts the person to have dementia, then it goes further and says if the person has Alzheimer's disease or some other forms of dementia. So that was the model. And the reason we collected all these different cohorts was we trained the model on a specific cohort, and then we use the rest of the cohorts to actually test the model, because we don't want the model to sort of really overfit, because sometimes these models do a great job if you show them the data and it trains very well. But when it comes to testing the model on a different setting, it may or may not do well. So we wanted to make sure our model actually is doing well on those cases which the model has not seen during the training process, right? So that's why we kind of split the 8 cohorts, so that one cohort was used for training and the rest were used for testing. So that what we call as an important step of computational validation of our model. But then the neurologists and the other clinicians actually helped us to validate the model further, right? So if you see on the right of this figure, you will see that we were able to sort of give, we recruited about 17 neurologists from all these different places, and then we gave them, each one of them independently, 100 cases. And these 100 cases had some form of dementia, some of them were healthy, some of them had mild cognitive impairment, and we gave them all the information about those patients, which means all the clinical history, the demographics, the MRI scans, the functional assessments, the same content that the model was trained on. The same content for each person on those 100 cases was given to these neurologists independently, and each one of them spent time to review those cases and then provided their assessment on those 100 people. And then what we did was we then compared our model on the same 100 cases using the same data, and then we sort of saw that the model was performing as well as those neurologists, the average neurologist, I mean. And we also did a couple more things. We then there is again, when we talk about neurologists basically has the skill to look at the different kinds of information like the patient history, demographics, and all that, and even sometimes imaging to assess the patient. But there is another class of clinicians, the neuroradiologists, who have the specialized expertise to look at only the brain images. So, so we recruited about 7 of them on an independent study, which is part of the paper, by the way. And what they did was they basically reviewed 50 cases of people who were already diagnosed to have dementia. So the neuroradiologist would know, already knew that all those 50 cases had dementia, but then they were asked to look at signs of Alzheimer's disease in those brains. And once they did that on those 50 cases independently, then we compared how our model also was able to identify those same regions in those 50 people. And then we sort of wanted to make sure that the model was able to pick the right signatures in the brain that was indicating Alzheimer's disease dementia or dementia due to other etiologies, right? So that's the other part we did. And then finally, on some cases, we also had post-mortem data. Some of these patients died, so their brains were autopsied and examined in detail molecularly, and we were able, and not we, but the pathologists who were trained to examine these brains graded each of those regions in the brain. There are many regions, typically thousands of regions, but I think they carefully selected about 100 different regions in the brain, and they looked at the pathology in those different regions in the brain, and then they graded the pathology for different kinds of abnormal protein deposition. And then we took all those um, cases in all those 100 regions and all the grades, and then we then also tested if the model was able to also predict pathology in those subregions within the brain. And that was again a very important thing to do, because we had a neuropathologic validation of our model. So that was kind of really the complete project. That is why it took us a couple of years. And I think it was an interesting process, because we just didn't want to end up doing a fancy AI model and then write a paper. We also were motivated to make sure the model is built, trained, and tested on different cohorts, followed by testing the model even further on based on clinical opinion, the neurologist opinion and the neuroradiologist opinion. And then finally, we also confirmed the findings on a few cases using gold standard data, which is coming from neuropathology. So that's kind of really the summary of the work. And most of the results that we presented, if you want to follow the order, I think figure 2 was mainly focused on making sure that, because we are collecting data from all these different sites, right? Because some sites may use Philips scanner, some sites may use Siemens scanner, some sites may use GE scanner to do the MRIs. We wanted to make sure there were no instrument related parameters that were influencing our models. So we had to extensively normalize and process all the data just to make sure everything fits in the same framework. So figure 2 was an important thing to present first, because we wanted to make sure that the site and scanner specific observations were not affecting the model performance. Followed by that, I think figure 3 was essentially showing how the model was performing in all these different tasks. Because like I said, the model was doing a two-tier task, right? The first tier was, it was trying to assess if the patient had dementia, or if the patient had mild cognitive impairment or normal cognition. So that was the first step. And then once the model identified it to have dementia, then we went further to look at if the dementia was due to Alzheimer's disease or due to some other etiologies, right? So figure 3 was essentially showing the performance of the model on the test data, which the model has not seen before. And we also used some latest advances in machine learning called as interpretable frameworks, which allowed us to identify which factors that we provided to the model were actually turned out to be important in terms of making the assessment. And what you see in the figures there is a list of those features, if you will, that we identified, the model identified in terms of making those assessments. That's kind of really figure 3. And one thing I just want to point out is that, interestingly enough, the MRI was not on the top of the list when it comes down to assessing dementia. MRI was actually number 3 in the list, and the first one was something called as a mini mental state examination, which is a very common cognitive test given to many people when they appear in front of a neurology clinic. So that was the interesting finding. But on the other hand, when the model was trying to differentiate between those cases who have Alzheimer's disease and the ones that do not have Alzheimer's but do have dementia, MRI turned out to be the top factor that actually made the model do that prediction. So that was kind of really the inference in figure 3. And as you go down in figure 4, you will see that we were able to sort of really dig deeper into the MRI scans and identify those specific regions that were highlighted that the model thought to be important in terms of differentiating between Alzheimer's disease, dementia, and other forms of dementia. And this was an important result because this sort of really confirms to the existing literature where something called as a hippocampus, which is one of the regions in the brain that is known to be known to be related to memory. So, and interestingly, the model was able to identify that as an important region in terms of making an assessment on those patients who have Alzheimer's disease. And not just hippocampus, I think we were able to sort of really rank order the importance of each specific region in the brain and its effect on making that prediction, which is supposed to be Alzheimer's. That's figure 4. Um, and figure 5 was, I think, probably again a very important result that we had to show, where we sort of again looked at those postmortem cases, and in each region, the expert pathologist was able to review different abnormal protein depositions called as amyloid and tau and all these. So what they do is they look at each region under the microscope and they grade it between 0 to 3. 0 being no pathology and 3 being severe pathology. And in each region they do it. And what we also did was we then predicted our model. We used the model to predict in those regions the risk of AD, and interestingly, the risk was sort of proportional to the grade of pathology that the pathologist identified in those people. And statistically, we showed that the model was able to consistently make that right prediction. And this is again what we call as neuropathological validation of our model. Right? And then finally, in figure 6, we kind of summarize the head-to-head performance of the expert neurologists who reviewed those 100 cases and how the model actually performed on those same cases. And interestingly, our model was as good as the average neurologist in terms of making the assessment. And we also reported something interesting because, shockingly, not so surprisingly, when we gave these 100 cases to these 17 neurologists, there was not a consensus in terms of the diagnosis and all these 17 among these 17 neurologists on every case. So it was interesting to see that, because you would think that every neurologist, probably trained in the same way, would make a same assessment, but it turns out not. So and on an average, we found out that the consensus on a scale of 0 to 1 was about 0.6 between all the neurologists. So that was an interesting finding we thought we should report. And yeah, I mean, finally, that kind of really summarized the neurologist level validation of our model. And it's kind of really what I did was I just basically tried to summarize the figures. But of course, there's a long list of methods that we have presented there. I'm happy to talk about that in more detail if anyone's interested. But in summary, again, yeah, I think the reason we worked on this project was we really want to build a tool. And we realized that if we have to build a tool, especially a clinical tool, that one day could hopefully be installed in a clinic, we want to not only just build AI models, but we want to make sure that these AI models are validated in the right way. And I think here what we did was we did 3 important things after building the model. One was we made sure that the model was validated on data that the model has not seen during training, from coming from many different cohorts, and then we took a consensus opinion on neurologists, consensus opinion coming from neurologists and neuroradiologists separately, and then we compared our model with their assessments, and then finally we made sure that the model identified regions of pathology also confirmed with neuropathologic evidence. And, and I think that was the reason why we were fortunate that this paper got accepted in a very good journal. And the feedback that we received from the journal was also very encouraging, because they appreciated the extent to which we tried to put all these pieces together to tell a compelling story, with the hope of one day to create a clinical tool. Yeah, I mean, I guess that's kind of really the summary of the paper. I know we are about 40 minutes into the meeting, so I can take a pause here and see if anybody has questions or any comments.
Yes, thank you so much for presenting your work in such a wonderful way that we could understand where data is coming from and how you're analyzing it. And yeah, that's it's really interesting work, and congratulations again. And please flash your microphones if you have a question. Yeah, go ahead. Thank you.
Thank you, Katrina, and thank you, Dr. Vijay, for such a great explanation. I just want to ask, because I also kind of stumbled upon um, mental health as my thesis topic here in Germany, and I got to
Mm-hmm.
work on micro expressions, dealing with stress and everything. And I was like trying to find the correlation how having excessive stress accelerates not only aging but also deteriorates the brain health.
Mm-hmm.
And I've kind of made some kind of tagging tools and everything, since you mentioned that you are looking for various ways to validate it.
Yes.
The thing is, like, AI can also be used to kind of predict beforehand that until what age you might get dementia, and
Mm-hmm.
also what kind of lifestyle you need to have. Like, you really need to include like pranayama or breath work, or doing guided meditation, having that 30 to 40 minutes of quietness throughout the day, and having that exercise and diet. Because I do see that such I have also come across studies that kind of helps in if you are able to manage your stress levels somehow, even though you're genetically more likely to get Alzheimer's, dementia, or even vascular dementia, because it's just not of the brain, it's even of other organs.
Mm-hmm.
So it's pretty fascinating. So my question to you is, do you validate via images or text data? And like, how do you see this beautiful mix of, the things coming from image processing AI, and how, like, biomedical is combining, and where is the future going?
It's a great question. Thank you for asking. I guess, first of all, I think the disclaimer is that I think we are just at the very, very early stages of really exploring the value of AI. I think there are so many things that can be done. Um, And when it comes to integrating data from images and data coming from, let's say, text or electronic health records, I think we are already doing some of that. Like at least in this paper, like I noted before, for us to be able to get the best information about the patient, we have built this framework to integrate both data that is imaging, like an MRI scan, as well as data that is coming in from neuropsychological testing and patient history and demographics, etc. Right? So we wanted to mimic a neurology setting. If what we wanted to do was we wanted to build a model that basically sees the same kind of information that a typical neurologist would see in a clinic, right? So which means it's all that kind of examination data, the demographics, patient history, and also imaging, right? So we are already kind of doing some of it, but of course, there are so many other imaging modalities and so many things you can do with imaging, as well as text data. And I think, yeah, the future, I think, is to be able to sort of integrate all this information in a meaningful way and an efficient way to be able to learn from the patterns. And to your other point about lifestyle, I fully agree with you, because lifestyles can make a lot of difference. In fact, I think if you talk to a neurologist, I have talked to a few, and most of them do agree that lifestyle modifications can hopefully, make a difference in the person's life. So I fully agree. Healthy work habits, healthy habits in general, I think can help the patient recover, or if not recover, at least even prolong the disease to a later stage.
Thank you for answering, and I believe that yeah, in future we will also need good multimodal systems, as these systems are known to efficiently, get, because as you mentioned that if it's taking so long to get an appointment from your neurologist, and as you also mentioned that people are living longer, and so it becomes like very imperative that if a lot of things can be done, like at simple centers or clinics before, like the doctor have like uh, you know uh, they put in more time and resource to diagnose, detect. If AI can at least eliminate that waiting period, I believe that we can if a good science collaboration happens, a lot of people can be like given an early warning and things like that. So thank you for answering my questions.
Yeah, thank you. And I also quickly noticed some of the comments on the chat. Um, Again, I probably won't be able to answer all, but at least just wanted to provide a quick summary to all the people who are listening. Thank you for those comments. I guess, I don't want to debate as to whether AI is going to replace jobs or take away something. I think it's not the question for me to answer, but generally speaking, I think there is a role for AI to play. Going back to my very first comment, I think if you're looking at a physician in Boston or New York City or one of those big cities, they're in good shape. They are the experts. They don't need to get replaced, and they'll probably never be replaced. But we're not talking about replacing jobs, but we're also talking about providing solution at a different clinical setting, at a setting where there is no resource, right? So there is a difference between the two. So in my opinion, I think the things that we have done in this paper kind of really talks about an important part, which is for us to be able to take, for example, a tool that hopefully can help somebody who is outside a main medical center and needs help. How do we build that tool? Right? We can't just simply build it from thin air. Right? We have to first of all make sure that we build a model or a framework that is validated from based on the gold standard. Right? So the process is, at least in my opinion, you want to take data, you want to collect all the information from the experts in places where there are resources. You build these frameworks, and once these frameworks are at least as good as these experts, which we have shown, then you have potential to take these things at different places, right? So I think the role of AI, in my opinion, at least the way I want AI to work is to build something, a technology that can be useful in places where there is a need, not to necessarily replace jobs. And I'll stop here.
If I may comment on that really fast.
I think Armish had the question, and yeah, let's just go in PTR if that's okay with everyone. Thank you.
Thank you, Katrina. Thank you, Vijay, for the presentation. I could just open the PPT PDF, and I have a couple of questions on the modeling approach.
Mm-hmm.
So the hybrid fusion model which we built. So I understand that the first step is the CNN, which takes inputs as those MRI images, and you get a score for whosoever would have likely to have dementia based just on the MRI images. And then in the second step, you build these tree-based models, and I saw you tried a lot of execution, a lot of tree-based techniques there, where you taking in inputs in, let's say, a tabular format for age, medical history. So image processing and everything is done at first step. Now you're just taking the tabular data of medical history, age, gender, and then you're running this tree-based model and likely to get those scores. Is that correct, or something else? Or is that
Yeah,
right
so
understanding?
I think that's a fair summary. Sorry, I couldn't catch some of the words you said, but that's okay. Yeah, I mean, I guess what we were hoping to do, like I said, was we wanted to mimic a neurologist setting, right? So a neurologist, for example, is not going to see the MRI first, right? Because the neurologist is going to first see the patient. And when the patient comes in front of them, they basically examine the patient. They look at all the history of the patient, and then they, based on their examination, sometimes they conduct some tests, and more often than not, they will get all the information they need when the patient is in front, and maybe from the electronic health record. So the information that the neurologist collects, it's not necessarily imaging first, but at the same
Correct.
time they can make an assessment. Some of the neurologists may or may not have access to MRI, so which means they have to somehow figure out a way to make a diagnosis based on patient's history and basic assessments that they can do in the clinic, right? So
Hmm.
the imaging comes at a later stage typically, because
Okay.
more often than not, imaging is basically used to rule in findings that are indicative of the disease or rule out some other things, right? So the way we constructed the model was we clearly knew or at least we tried to appreciate the workflow. So we trained the CNN on the MRI, and we
Okay.
then fused the MRI based features that were trained on the CNN with the non-imaging data to then fuse the information together to make an assessment.
Correct. But here's the confusing part. So I understand their first level of modeling just tries to identify the probability of dementia, and then you have sub models within those. Is that right?
Yes. Mhm.
Yeah. So okay. So what you're saying is that the whole CNN plus the tree structure actually ends up a complete. This actually is the first step, which identifies the dementia, and then you have separate models, maybe different approaches, to do the same.
Um, so so we have models where uh, we do both the steps using non-imaging data. We also have models that we showed that does that using imaging data. We also have presented models where fused information also does both the steps, right? So it's not just one model that we created. So we want to make sure we run on all the different combinations that exist, where you have a non-imaging model, and you have an imaging model, and you have a fusion model. All three are making the same assessments.
Got it. Got it. Just one last supplementary question.
Mhm.
So, what sort of benchmark you have in this in your field? Because I saw the accuracy number. Just there are 73% accuracy for one of the models. So, is it like a good benchmark,
Where,
or
where, where were you seeing 70%? Can I ask?
in a PDF I just saw there is a number against? I'm not sure if it is against
Yeah.
accuracy or.
Yeah, so again, we can go into the details of the numbers. So that's a very important question and a great question, right? So I guess it's hard to think about a standard only because what we are doing is research at this point, right? And I think hopefully standards are going to be established in the future. But that being said, uh, that's actually one of the reasons why we validated our model to see how it compares with the average neurologist who is actually seeing patients, right? So the way I would think of a standard is to see if the model is doing at least as good as the expert. And I think we achieved that goal because like I said, we gave a few cases to these neurologists who were located at different places around the world, and each one of them independently reviewed all these cases and provided a standard diagnosis, right? And what we did was we compared our model on those cases, and then we show the results where our model at least meets the basic standard of an average neurologist. I think, which is again one step, not the only step to do, but I think that was encouraging.
Thank you, Vijay.
Yeah, Dr. Shah, did you have a question? Okay, maybe she's away from the phone. Sandeep and Dr. Keisha, welcome. Do you have a question or comment? Isn't my voice like, can people hear me well?
I can hear you.
Okay.
Yeah.
Joyce, do you have a question maybe?
Oops, I'm so sorry. There was some problem at my end. I apologize. Am I audible now?
Yes. Mm-hmm.
Yes.
Perfect.
Right. I'll be sounding extremely dumb because I do not know what happens medically in case of dementia. But yes, I'm pretty excited about the technology discussion. I want to say thank you, Vijaya, for sharing the knowledge about the research that is happening in AI space with regards to dementia.
Hmm.
Very quickly, just wanted to understand if it comes about implementing AI solution for doctors to utilize this technology, how much time are you looking at this will become viable for commercial usage?
It's a great question, Sandeep. Thank you for asking. I sometimes think about it, but I don't think I can answer that at this moment because there's so much to do. There's so much to do. I mean, I think like maybe somebody else also asked the question, right? So where is this tool going to be useful, right? It kind of really points to the other part, which is AI replacing jobs or whatever. The fundamental point to keep in mind is that we have built this AI model based on data that we collected in rich medical centers, and by comparing the model with experienced neurologists who are in these medical centers, right? So this was sort of really an important proof of principle for us to establish to make sure that people are convinced that a model like this can actually do the job right. Right, so that's the only thing they have accomplished. But I think if for this model to actually become a tool that's going to be useful in a clinic, there are multiple things that have to happen. First of all, we have to actually, we can't give an AI algorithm to a doctor, right? We have to somehow build a software. We have to somehow figure out how these things are going to work in a clinical workflow. And there are so many clinical workflows around the world. And more importantly, the question is, where do we put the software? Do we put the software in Boston, or do we put the software in a primary care center, in many different primary care centers, right? So I think the real value of this model or this software, and one day if there is a software that can be built on this, is when this software can go upstream in the clinical care continuum. When I say upstream, I'm talking about primary care centers, general health practices, and those places, because those are the places where you don't have neurologists, you don't have abundance of expertise, right? So, but for us to go upstream, we have to make sure we do all the studies downstream, which means in a clinical center which has the right expertise, right? So we are only at that stage at this point where we have a proof of principle that this can work, right? So what I'm hoping in the future is to sort of really think about those upstream tasks. And at that point, maybe I think that question that you asked, which I think is very important, is to think about how can this be, a tool that can be either commercialized or that can be useful in a clinical setting. Sorry, I don't know if I answered your question completely, but
No, no, absolutely. I get it. It's very difficult to predict the time right now. But a quick question. I'll keep it very brief. Uh,
mhm.
you must have an idea by now that whether this technology, the AI technology that we are looking at, is it going to make the overall uh, treatment expenditure go on a higher side, or will it bring it down? What is your view on that?
Well, again, uh, in a simple if calculation, if I have to do, right, a neurologist's time is very precious, right? And first of all, we don't have many neurologists, right? So clearly, if you're really counting by the dollars, right? So a neurologist probably is going to cost more money than a primary care physician, or just an appointment in a neurology clinic is probably going to cost more than an appointment with a primary care physician, right? So So if I have to just do that simple math, and if I have a tool that can sit in a primary clinic but maybe costs much less than the average neurologist clinic, then maybe we are already beginning to think about saving costs.
Thank you so much, and want to appreciate entire group here for conducting such a beautiful discussion. Thank you so much, Vijaya.
Thank you.
Yeah, thank you. I hope you do you have time for one more question? I know that
Sure.
Mitch was
I do.
asking.
Yeah.
Perfect, thank
Mm-hmm.
Hi Vijaya, this is Mitch from Sweden.
Hi.
Just a quick question. Really great work, and I am so grateful.
Thank
Dementia
you.
is a very personal disease for many of us, especially for people that we love. I am just curious. Are there many markers or tests like for the elderly, like for example the time up and go test, more for gait and fall detection? Are these many tool sets or data that you collected seamless or available in the many standardized tests for the elderly, making it much easier to broaden its diagnostic tools, since the the government already sort of has these protocols? Or are there special, is your test more specialized, which means you've got to draw even more data points from the
I see.
elderly? Or yeah,
I
just
see.
wondering the practical aspect of data
Yeah, that's a great.
collection.
I,
Yeah.
I, I think you're asking a very important question. I think I understand what you're asking, which is, we've done these models using some tests, using data coming from some standard tests, right? So, what you're asking is, maybe those are not the same tests that are done everywhere, or maybe there are different tests that are recommended by some governments or some hospitals, right? So, how do you account for that, right? So, that's a great question. I guess part of the attempt in this paper was to not just create a single framework or single model, sorry. What we realized is that clearly, if you have a tertiary medical center which has all the resources, they do all kinds of tests because they have the money, they have the resources, they have the expertise. Whereas, if you go to a place, maybe a remote clinical setting, they probably don't even do an MRI. So then how can one single model be useful for these two different settings, right? So we are aware of that, and which is the reason why at least we attempted to create a series of models uh, with flexible combinations of data to actually show that regardless of whatever combinations we have used, we are still able to get a reasonable result. Of course, we have not exhausted of all the possible tests, but at the same time, we are also not trying to recommend a set of tests that have to be done, right? So it's a careful balance. I don't think there is a perfect answer, but we do realize there is a potential for that discrepancy that can exist in different places, right? So I think these are the practical issues. These are exactly the practical issues that we need to solve, because we can't just expect AI to just work on everything, right? So these are the practical challenges, and we have to figure out a way to somehow make this tool work in any different setting, any clinical setting, right? That's the biggest challenge, right? At this point, it works in a few settings, but probably not all. But I think we are on the right track.
thank you. Sorry, did you want to follow up, Mitch?
No, thank you. Just thank you so much.
I know that I oversaw Dr. Keisha. She had the question earlier. Please go ahead if that's okay with you.
Thank you. Vijaya, thank you for being here. I'm a pathologist in the United States, and I'm glad you incorporated the neuropathological diagnoses and correlation
Mhm.
in the study.
Thank you.
But I want to know about acceptability, because what I'm noticing, I did a lot of consultation for AI for pathology diagnosis for prostate and breast cancer. And
Hmm.
then once we go through it, a lot of it's promising is that there's still a lot of older pathologists and older doctors that don't want to, when you bring it to them,
Yeah.
incorporate it into their practice at all.
Hmm.
So what do you think about trying to get it to something that's actually accepted by by colleagues?
It's a great question, and thank you for promoting AI in pathology. That's a tough one. I agree with you. In fact, all my mentors, they still see slides under the microscope. They don't want to touch the computer. So you're absolutely right. I think the generation that the experienced pathologists, they're all used to seeing things under the microscope. I think with respect to this paper, I want to make a comment that we only used neuropathology as a way to validate our model. So the technically the digital pathology aspect is only for validation, because as you know, if patient is alive, you can't get a slide for that brain biopsy, right? Because nobody does biopsies on brains, especially if they have suspicion of dementia, right? So the role of pathology in our paper was only to validate, but I think your question was more broadly about AI and digital pathology, which is a completely different topic. And I think from what I understand, I think people are slowly beginning to appreciate the value. I think there is a lot more we need to do to be able to somehow, digitize the whole world of pathology. There are some clinical centers who have begun to, I think, go fully digital, but not all of them. Maybe less than 5%, if I have to guess. But it's a very hard task to convince those senior pathologists to completely change the way they do things that they have been probably doing for decades, and stop ask them to stop seeing things under the microscope and certainly ask them to see things on the computer. So that's a very tough thing. I don't know if it's going to be possible, but hopefully the future generation can adapt easily with the new digital world.
Yeah, thank you so much for your time. I know we've gone a little bit over an hour. I hope that was still okay for you. And thank you so much for sharing your really interesting and also very helpful for the future work, and for answering our questions. It was such an interesting discussion, and we really appreciate your time. And yeah.
Thank you for hosting us, and I'm so happy to have met some of you, and thank you for the time that you have given me.
Yeah, we really appreciate it, and thanks everyone for coming, asking questions, and for sharing, commenting. And yeah, if you like discussions like this, follow the club. We will have more guest speaker events in the future. So we will have um, tomorrow Dr. Kirev coming at 10 p.m. EST, talking about e-tattoos for continuous blood pressure monitoring, which is really important. It's a really important indicator for health. Um, and on Friday, we'll have Dr. Kim Lafay. She will talk about thymocyte cell type discovery and leukemia. And next week, we have a lot more rooms. Dr. Michael Levine will be coming, that made these xenobots, and he will update us on his current lab research that's still not published. So um, yeah, thank you so much, Doctor, for being part of this group here and this club, and for sharing here. And we really appreciate it, and we hope you come back one day. And we wish you all the best for your work and all the funding and intelligent people joining your lab to advance your research. Thank you.
Thank you so much to all, and thank you, Katrina. Take care.
Okay, thank you. We'll close the room in 3, 2, 1. Bye, everyone.